I want to do a calculation with you to just do a little review of how we do our E-field calculations. So I'm going to actually use the Jamboard and give you a standard E-field calculation and talk about net E-field. So I'm going to give you a charge here. This is a positive charge. I'm going to define the charge with a known 4.5 microcoulomb charge. So out here, some distance away from that charge, is a point in space. We're just going to call it point P. The point. There is no charge there. It's just a place. So we can't talk about the force on point P because there's nothing there to feel a force. But even though there's nothing there, we can talk about an E field at point P. So if I call this charge charge A, the E field that I'm talking about from charge A is going to be calculated as E equals K Q over D squared. There's only one charge, charge A, because there is no charge at point P. But the distance I'm talking about, if I want to know the field strength at point P, is still the distance from that charge to point P. So if I say, hey, what's the strength of an electric field at this point in space? What I want to know is how far away is point P, the place in space, from charge A? That's 12 centimeters. It's like, oh, okay, now I can calculate the field strength. The field strength is K, which always changes, or is never changing. It's always the same. 9 times 10 to the 9th Newton meter squared per Coulomb squared. That's the Coulomb's constant, always. And then my Q is the charge that's creating the field, which is my 4.5 microcoulombs. And since it's microcoulombs, I know I have to make that times 10 to the minus 6 coulombs. And then all of that is divided by the distance from the charge to the point in space, which is 12 centimeters. So it's going to be 0.12 meters, which has to get squared. So there's my setup. Now, because this is an E field strength and not a force, the final units are going to be newtons per coulomb. It's not a force, it's a field. So I'm going to get newtons per coulomb. So let's do this. Let's actually throw this into the Desmos calculator and make sure that we can get the calculator to run the numbers that we want. We'll do Desmos Scientific, and I'll just actually put those things in. So here's our calculator. I'm going to say 9.0 times 10 to the 9th. 9.0 times 10 raised to the power of a to the b, 9. There's 9 times 10 to the 9th. Times my charge. And my charge, QA, is 4.5 times 10 to the minus 6. So we'll put that in, 4.5 times 10 raised to the power of a to the b minus 6. Okay. Now, I'd like to put all that in parentheses so that I can divide it by my distance squared. My distance, remember, has to be in meters. So the 12 centimeters becomes 0.12. So divided by 0.12 meters. But that's got to get squared. Here we go. So it's a really big answer, 2,812,500. So my answer here is 2,812,500 newtons per coulomb. Now, the reason it's so big is in part because a coulomb of charge is such a big amount of charge. So 9 times 10 to the 9th times 4.5 times 10 to the minus 6 is my KQA divided by the distance squared. And there's my field strength. So what if I now say, well, I'm going to put a charge at point P. What if I say, now that I know the field strength, what's the force on an electron that I place there? So let's say, all right, put an electron, P minus, at P. What force will it feel? Now I can just say F is E times Q, because I know the E field already in newtons per coulomb, and if I define the charge that I put there, I can find the force on it as E times Q. And an electron always has the same elementary charge, 1.602 times 10 to the minus 19 coulombs. So once I know the field strength, E, it's very easy to find the force on any charge that I put at that point. So I'm going to stop there, but that was a simple reminder of how we calculate the strength of an E field at a point in space when I know the charge creating the field and I know how far away the point in space is. If we were going to do a net E field, just like net force, we'd have to make that calculation twice and then either add or subtract. And that's a little bit more involved, but that's a really good fundamental basic way to think about how we do our E field calculation.